And thank you, Valerie, and the AIVC for offering me the opportunity to talk about some of the research that I've been doing with Dr. Ben Jones. In this talk, I'm going to be talking about using pathogen-free air to reduce infection risks in buildings. This work was sponsored by the AirBods Airborne Infection Reduction through Building Operation and Design for SARS-CoV-2 project. It was a UKRI-funded project led by Professor Malcolm Cook at Loughborough University and was a conglomeration of several universities around the UK whose aims were to quantify the risk of transmission of SARS-CoV-2 in buildings. Today I'm going to be introducing you a mass balance model and then discussing the uncertainties in viral emission rates and why that makes it difficult to predict absolute risks of infection. I'm then going to consider both personal risk and population risks. First of all, we have a mass balance model, which it enables us to try and establish what an inhaled dose might be by calculating what the concentration of a pollutant in a space, and in this case, it's a virus. So the virus will be emitted into the space from an infected individual through aerosols, through talking and breathing. But these virus encapsulated aerosols can be removed by ventilation. The virus can be rendered unviable by biological decay, either natural decay or via things like UV light, which can increase the biological decay. And also, we can use filtration to remove the particles, and some of the particles will be removed by momentum-induced deposition and sorption. So for our mass balance model, we have the gains, the emission from a person, and the losses: dilution via ventilation, surface deposition, biological decay, respiratory tract absorption, and filtration. Now, all these removal losses are expressed in terms of air changes, and they can be summed together to give us a single value, which we term phi. And that enables us to establish the steady state number of viral copies in a space, given an emission rate in viral copies per second, and this removal mechanism phi in per seconds as well. Now, this is the total number of viruses in the space, not the concentration. So we have to divide through by the volume to get the concentration of the viable viruses in the space. And this is important because the dose is proportional to the concentration of the virus in the air. Now, as I mentioned before, there is uncertainty in the viral load, and this just illustrates how the viral load of an infector changes over time. So I have a zero time here, which is the days of symptom onset, and you may be infected up to 5 days prior to symptoms. So you have this pre-symptomatic phase, and the viral load will increase. It peaks just after onset of symptoms, and then it will start to decrease as the immune system starts to battle and tackle those viruses. So we have this heterogeneity in the viral load through time for an infector, but there's also great heterogeneity of viral load from person to person. So some people have exceptionally high viral loads and other people have really low viral loads, and we don't really understand why this is. This is some data that's collected from NP swabs. So we're just measuring the viral load. I'm particularly interested in the non-severe COVID patients here, and the spread of viral load 2 days after symptom onset ranges from 10 to the 12 down to 10 to the 3 RNA copies per mil from these PCR tests. This is not a new thing, this kind of difference in the emission rate of pathogens. Here's a historical perspective. Back when Riley and Wells were doing their studies on TB, that they discovered that there was variability in the infectivity of different patients, and it was far greater than they realised. 2 of the patients produced 19 out of 22 infections, even though 62 patients occupied the ward. The astounding infectivity of these 2 patients in comparison with the others was related in part to the infectivity of their sputum. And comparably, in 1978, Riley, where they established the Wells-Riley model by modelling an airborne spread of measles in a suburban elementary school, discovered that the index case may have been exceptionally infectious because the number of secondary cases that they had were on average about 1/10 as infectious. So maybe for many pathogens, we have a range of emission rates from infectors. Because of this high uncertainty in the emission rates of a virus, we first established a relative exposure index where we calculate the inhaled dose of occupants sharing a space with an infector compared to a defined scenario. In this case, we used a UK school classroom. And this meant that the uncertainty in the emission rate cancelled out, because actually what we're looking at is just a ratio of doses that were inhaled. And that would enable us to say that given a infector, we could compare how the dose would change dependent upon the scenario. So given the same infector, in the reference case, if that same infector was in a supermarket for 1 hour, then the inhaled dose would be about 1,000-fold lower than if you'd shared a classroom for 7 hours with the same infector. Likewise, if that same infector had been in the Skagit choir singing for a couple of hours, then the inhaled dose might have been about 10-fold greater than it would have been if you'd spent 7 hours in the reference case. So this is our relative exposure index, but it gives us no idea about the absolute risk. For example, there may be no infectors in the space, or the infectors may have a low emission rate of virus in the first place. What it does allow us to do is to see how ventilation might reduce the relative exposure risk. So here's just our school classroom in the UK. We ventilate at 5 litres per second per person, which is why the relative risk is at 1 at that point, about 160 litres per second. But what you can see is there's a law of diminishing returns, because the relative exposure index is inversely proportional to the ventilation flow. And that means that we get the better effect, better bang for our buck by increasing the ventilation rate in very poorly ventilated spaces. So you can see here, by adding the first 100 litres per second of ventilation, we get a reduction from about 3.5 down to maybe about 1.3 of our relative exposure index. To add another 100 litres per second of ventilation into the space only reduces it from about 1.3 down to about 0.8. So you can see for every additional 100 litres per second of air into the space, we get a reduced impact on the relative exposure index. And that has consequences, because overventilation in winter can lead to occupant discomfort and excess heating energy, maybe even undesirable user behaviour. We now turn our attention to compare two different spaces when we look at personal and population risk factors. Here we have a 5-person office, and the relative exposure index here is 10 times greater than a 50-person office. Here we've set the relative exposure index to 1 to represent this 50-person office. Both of these spaces have exactly the same kind of characteristics: 30 metre cube per person, and it's supposed to be 10 litres per second per person. So apologies for that, but it's 10 litres per second per person, and this is equivalent to 1.2 air changes. So in total, the total removal is an equivalent ventilation of 2.2 air changes in both spaces. But because the 50-person office is much larger, that's 920 litres per second compared to 92 litres per second in the 5-person office. So given the opportunity to share a space with an infector, with a single infector, I would rather share a 50-person office for a personal perspective, because I know that my inhaled dose would be 10-fold less in the 50-person office than it would be in the 5-person office. However, how do we know if there's an infector in the space? It's just like pulling balls from a bag. Different coloured balls give us an opportunity to estimate how likely it is to be sharing the space with an infector in the first place. And as you can well imagine, the possibility of sharing an infector in a 50-person office is much greater than in a 5-person office, because there are more people. Here we assume a community infection rate of 1%, and we can see that in both spaces, the most likely number of infectors in the space is 0. So you're most likely to not have an infector in the space. The second most likely number of infected people is 1. So in the large office, that's around about 30%. And in the small office, it's around about 5% of the time you may be sharing that office with an infector. I can demonstrate this. Here's a population of people. All these squares represent people in a population, and the orange represents 1% of that population who are infected. I'm going to split this population up now into 50-person offices. And as you can see, when we divide these into these spaces, only a subset of that population are susceptible because they are sharing a space with an infected person. Many of the spaces here, these occupants are not susceptible because there's no infected person in the place. So it doesn't really matter what the ventilation rate is because there is no emission of virus into those spaces. However, if we were to take that same population and split them into 5-person offices, you can see that the proportion of that population that is now susceptible is greatly reduced, represented here by these orangey bars. Let's go back to that viral load and the uncertainty in the viral load. We can make some assumptions about this viral load per mil of respiratory fluid, and we can measure the volume of aerosols that have been emitted by people who are speaking and come up with an emission rate per hour in terms of RNA copies per hour. And here we have a probability distribution function based on this data that shows that the most likely emission rate is for about 100 RNA copies per hour. But you have people emitting at almost a million copies per hour as well. This is the cumulative frequency. We can test how likely this model is with actual data. There's been 4 studies now that I'm aware of that have used these G2 devices where they've taken COVID patients who've done a variety of talking and singing and breathing activities and collecting the aerosols that they've emitted and counting the number of RNA copies. But this method is restricted because it has a limit of detection, so it can only detect 75 copies per hour or more. Below that threshold, the way that the methodology is set up, it can't detect it. And for this modeling exercise, I assumed a value of 1 for all these experiments where there was 0 or no detection of any genomic material. But what we're able to do is by comparing the cumulative frequency that we can see that there is a good alignment with the model and the actual data that was collected from these G2 studies. It's interesting to note that over 60% of the people, or the COVID patients that take part in these experiments have emission rates that are below the level of detection, so below about 75 RNA copies per hour. Okay, so once we've got this distribution of viral loads, we can then use a dose-response curve, which will enable us to try and calculate the probability of a susceptible person being infected. So given these an infector with these viral loads and the emission rate into a given space, an office, a 5-person office or a 50-person office, we can then use a dose-response curve, a dose-response constant, to determine the probability of the susceptible people becoming infected. The green bar here shows the distribution of those viral loads on the right-hand axis, and on the left-hand axis, it's the probability of infection. We can see here for a 50% probability of infection, you need a lower, or you can get away with a lower viral load in the 5-person office than in the 50-person office. If you recall with the relative exposure index, the relative exposure index was 10 times higher in the 5-person office. So that's why you can get away with infectors with a lower emission rate that will lead to an infection. You need to put more virus into the 50-person office than you do in the 5-person office. So you can see here that there's a greater proportion of infectors able to infect in the 5-person office compared to the number of infectors that are able to cause 50% infection or more in the 50-person office. We can combine these probabilities into something that we call a proportion of people infected, which is given in this value, given in this graph here. And the way that we come up with these values is to take the probability that an infector is present. So if you recall, the probability of an infector being present is much greater in the 50-person office. And that gives a much greater proportion of the population that is susceptible. The probability that the infector has a given viral load, these are the viral loads along the bottom, and the probability that that given viral load gives rise to an infection. The ratio under these curves we call the transmission ratio. We call it the PPI, and the ratio is the transmission ratio. So for a 5-person office, the area under this red curve here is about a third the area under the blue curve. So that would mean that at a population scale, the 50-person office is approximately about 3 times more risky than a 5-person office in terms of the proportion of the population who would be infected. So given a single population, either split into 5-person offices or 50-person offices, that you would get a greater number of transmission events in the 50-person offices than in the 5-person offices. We don't know the absolute values because there are some uncertainties and some of the assumptions that we have to make, but you can read more details about that in our paper. We're also able to explore some of the uncertainties in the values. So here we have the REI, the relative exposure index, and the PPI, the proportion of people infected. So you can see from the individual risk, the 50-person office is much lower than the 5-person, but from the population point of view, the 50-person office is slightly more riskier than the 5-person office. What can we do with ventilation? Here we look at the proportion of the population infected. With a 5 and 50-person office, again, we can increase the ventilation rate per person. And we get this kind of law of diminishing returns. And we can see here that if we try to bring this blue line, which is the 50-person office, right down to the levels that we would see in the 5-person office, we'd have to put an extraordinary amount of ventilation into the space to have an equivalent risk as a 5-person office ventilated at 10 litres per second per person. So again, this shows the impact of reducing those of targeting those poorly ventilated spaces and getting them adequately ventilated rather than going to over-ventilate spaces in terms of elucidating an effect. This is the same graph, essentially comparing the transmission ratio. So a transmission ratio of 1 would mean that we have an equivalent risk, and you can see it would have to be somewhere in the order of several hundred litres per second per person in order to get an equivalent risk between a 50-person and a 5-person office. However, we are able to get an equivalent risk by reducing the occupancy in the 50-person office. So maintaining the space volume and maintaining the 500 litres per second, we can get about 14 people into the 50-person office, and it would have an equivalent risk as 5 persons in a 5-person office. So reducing occupancy is a good way of reducing the risk at the population level. Community infection rate also has a dramatic effect on the proportion of people infected, because as the number of infectors within the community increases, so does the probability of sharing a space with an infector, which increases the susceptibility population. So what next? We need a new focus on IAQ generally, particularly targeting those poorly ventilated spaces. However, there are limits to what we can do to make a building resilient. There are limits to the effect that ventilation can have on transmission risk in buildings, because we don't have any means of affecting the community infection rate. Some infectors have high emission rates, so even if we try to ventilate really well, that there's still going to be such a vast amount of virus being emitted into the space that the doses that susceptible people are inhaling are going to be sufficient to render them infected. And then there are other issues like social distancing. Personal and population risks are different. And when a building is occupied, there is no such thing as a zero risk, because we can never tell if an infector is present or not. We must reevaluate existing ventilation systems and particularly identify those poorly ventilated systems and try to improve them. And we must consider behaviour, ensuring that people use systems appropriately. Many buildings have design capabilities to be well ventilated, but if people don't understand how those ventilation design strategies are to be used, it might not be ventilating as appropriate as the designer might have anticipated. And regulation, perhaps periodic demonstration of performance, like they have in Sweden, might be a useful way to ensure that buildings are maintained and well ventilated. So thank you very much. I'm sure if you've got any questions, my colleague Benjamin Jones is around at the conference, and I'm sure he'd be more than happy to talk and discuss these things in more detail. Thank you very much. Our publications are available, some links there to the 2 papers that I've focused on in this study. And thank you very much.